Okay, dear students, so welcome to this video. In this video, we are going to learn about the Wien's law, and that's it. That is the last law that we are going to cover in this topic. B1. Okay, so Wien's displacement law is the complete name of it. First of all, displacement is not written here, by the way. So it's Wien's displacement law. Okay. Now, what is happening is like this is the second part of the same thing that earlier we talking about. I told you that if there is a body and we are heating it up and it is attaining certain temperature, so it is seen that whatever is the temperature, these such kind of bodies they keep on changing their color. Like hotter the body is, it starts becoming red and then yellow and then bluish, and when it is becoming very hot, it starts looking whitish, although if it is not heated it looks grayish. So it's usually a metal, so it looks gray when it's not heated, but once it started heated up it has various colors, all the colors are coming out. So even that is one of a phenomena that we are curious about, like why is that happening. So this is happening because of the Wien's displacement law. Now Wien's displacement law is something like this. So, point number one that you have to understand here, according to the law, is that whatever be the temperature of the body, whatever be the temperature of the body, it will be radiating the complete spectrum. So it is already radiating all of the colors and everything, like all the radiations which it has once absorbed sometime, all those radiations will be emitted back because it doesn't want to basically increase the temperature, you can say, or it wants to come back to the same temperature. So it is now radiating. So it is radiating all of the energies which it once absorbed. Now, the point number one is all wavelengths are there in the spectrum. All wavelengths are present in the spectrum. So all the colors are there: red, blue, green. I'm just talking about the visible light. So all the visible colors are present there. Some countries they are calling it Vibgyor, and in some countries it is called Roy G. Biv. So whatever way you want to learn, like a kind of rainbow colors, so all the colors are there, and all the colors are being emitted. But what happens is one color or one particular wavelength is having the maximum intensity at particular temperature. It was found that, like, let's say we are concentrating on 3500 Kelvin. So when this metal piece was brought to this temperature, it was seen all the wavelengths are being emitted. All the wavelengths, like this is going to infinity. So all the spectrum is there and all the radiations are being emitted, but there is one particular wavelength for which the intensity is found to be maximum, like what is on the y-axis, spectral radiance. So it is kind of a intensity, you can call it. We do not want to go into detail, it is very complex phenomena. It would be using stradian, that is like one angle is radian, and then there is a solid angle which is known as stradian. So it will be talking about the stradians also, so we are not concerned with that. So you can just call it intensity of the light which is emitted. So the intensity of one particular wavelength is found to be max, which means that for 3500 Kelvin, all other colors are lesser. Red color is maximum. Let's say this is red. So at this moment, the body will be looking reddish. It will be having all the colors, but it will be looking more reddish. Now, as the temperature keeps on increasing, what is seen here is like gradually it keeps on moving towards the left hand side. So there is a displacement of this. We're talking about the lambda max. Now try to understand what this lambda max is. This is a misnomer. It's not the maximum possible wavelength. It is the wavelength of the light for which the intensity is maximum. It is written as lambda max, which usually means the maximum value of the wavelength. But no, it is not that, because this wavelength is bigger, this is lesser, no doubt about it. So as we are moving leftward side, the wavelength keeps on reducing, and that is why here the color is red, and for the last one the color will be kind of, they have shown green, and you can call it blue or violet kind of band. So it will start moving towards violet, from the red to the violet. Okay, so it is moving like that. So this is lambda max, which is the wavelength of radiation for which the intensity or spectral radiance is maximum, for which the spectral radiance is max. So the intensity of that particular color is max. So coming back again to the diagram, it is 3500 Kelvin. The temperature increases 4000, 4500, 5000, 5500. So what happens at this temperature? Clearly, this wavelength has moved towards the left. There is clear cut displacement of the lambda max. That is what is known as Wien's displacement law. So it is displacing itself towards the left hand side. So the color is becoming, it's going towards violet. So concentrating on this green, so you can clearly see, if I say this is red color, like this particular wavelength is belonging to red wavelength, red color. So red color intensity has also increased. Earlier the intensity for the red was quite low. Now the intensity of red is much more than what it was for the earlier case. But now the body will be looking greenish, bluish. The body will not be looking red in color, it will be bluish in color. Why? Because the intensity for the violet color or for the blue color is maximum. So it is looking more bluish. Okay, although even red has maximized. Okay, all the colors have maximized. All the radiations are obviously they are having higher intensity now as the temperature increases. No doubt about it. So this is the law. How do we write it mathematically? Mathematically, the product of this wavelength, again I'm repeating, please, this is a misnomer. It is not the maximum wavelength, it is the wavelength of the radiation for which the intensity is maximum. That is lambda max. Now the product of lambda max and the absolute temperature of the body, it is always having a constant value which is 2.9 10 raised to power negative 3 meter Kelvin. It is not milli Kelvin. Okay, it is meter Kelvin. So be very careful with the units. And if you write it with K capital first and then small m, people might read it as kilometer. So this is not kilometer, it is meter Kelvin. So be very careful. This is the unit, and like meter is coming from the wavelength, Kelvin is coming from the temperature. So lambda max into T is equal to 2.9 into 10 raised to power negative 3. And accordingly, because it is a constant value, so more is the temperature, lesser becomes the wavelength. So lesser wavelength means more frequency. It means the color will be changing from red to violet. That's it. This is the Wien's displacement law. Okay. All the best. Bye.